Welcome to the Deep Dive, your shortcut to becoming well-informed. Today, we're zeroing in on flying robots, a field that's really buzzing with innovation, and it's all thanks to your curiosity about it.
And our exploration today, well, it's based on this research paper, Flying Robots for a Smarter Life. It's by Dr. Abdellatif Baba.
Yeah, from Kuwait College of Science and Technology and the University of Turkish Aeronautical Association.
That's the one.
Exactly. So our mission, really, is to pull out the most, fascinating insights and the real-world possibilities these flying robots offer, trying to make our lives smarter without getting too bogged down in the super technical stuff. Okay, so this paper, it kicks off by painting a broad picture, and honestly, it's pretty eye-opening.
It really does. The paper highlights how these flying robots, you might know them as UAVs, maybe multicopters, they're increasingly seen as, well, key players in boosting our quality of life.
Especially in smart cities, right?
Exactly, especially in our growing smart cities. And look, this isn't just theory anymore. The progress has really, really accelerated recently.
It feels like it's moved way beyond just being a cool gadget. The designs themselves are becoming incredibly adaptable.
Yeah, flexible.
And the research points to some seriously practical, intelligent tasks. Things that are either being developed or, in some cases, already happening.
Like what kind of tasks?
Well, think real-time surveillance. That's kind of obvious, maybe. But also emergency and rescue missions, tackling fires, and even delivering goods. Package delivery drones.
And what's fascinating here, I think, is the paper's recognition of the impact, the significant impact this tech is having and is going to have on society and the economy.
It really flags it as a vital future trend.
Absolutely. And when you think about how cost-effective and flexible UAVs can be, I mean, they can get to places that are difficult or dangerous for humans.
Right.
It's easy to see why they're taking off, so to speak.
Yeah, exactly. And that leads us nicely into some of the really novel designs the paper talks about. This is where it gets interesting, I think. Forget the standard drone image for a second. These are specialized machines built for very specific jobs.
Okay, like the first one. A quadcopter designed to automatically mend our smart grids. That's pretty wild.
It is. Imagine a flying robot like you see in their figure 1, not just with cameras, but with 2 actual robot arms. And grippers.
Specialized grippers, yeah. So like a flying repair person.
Exactly. That's a great way to put it. So the whole idea is for these robots to fly up and, independently check the vital parts of our smart grids.
Things like transformers, isolators.
Control units, even the high-power cables themselves.
And it's not just looking, right? The paper says they're designed to actually do repairs.
Yeah, perform maintenance. It details their ability to do things like cable jointing or even swapping out components that have failed.
Wow, and those grippers must be crucial for that.
Oh, totally essential. They aren't just hanging on. They provide, rock-solid hovering stability while these, delicate operations are happening.
Like having a perfectly still robotic technician just floating there in the sky.
Precisely. Okay, then there's another really innovative concept.
Yeah.
The liquid transporter. It's shown in figure 2.
An octocopter this time, so 8 rotors.
Right. And it features a 10-liter tank, plus a robot arm that can move 360 degrees, any direction.
10 liters is a fair bit of liquid. What kind of tasks are we talking about here?
Well, really crucial stuff. The paper mentions firefighting, spraying pesticides on infected crops, and even something as practical as painting building facades, like color washing.
Okay, but hang on. With a freely moving robot arm and all that sloshing liquid, stability must be a massive challenge, right?
Oh, absolutely. A huge challenge. So the paper explains they've developed this clever system using something called fuzzy logic.
Fuzzy logic.
Yeah. And this system, it constantly adjusts the lift force, the power, to each of the 8 rotors.
To counteract the movement of the arm and keep the whole thing steady.
Exactly. Keeps it balanced.
And I noticed in the figure, it has 8 energy harvesters, too, 1 on each rotor support. Why so many?
Good question. Well, octocopters, they tend to use a lot of power. So these harvesters are there to basically optimize energy management, make the most of the available energy, maybe extend its flight time.
Right, maximizing efficiency for a power-hungry design. Smart.
It really seems incredibly well thought through. Now, obviously, powering these impressive machines requires some equally impressive hardware.
Yeah, the guts of the machine.
Exactly. The paper gives us a peek. Table 1 has specifics, but one thing really stands out. Computer vision is absolutely fundamental.
It's the key, yeah. The paper really emphasizes that high-quality color images are essential.
Mm-hmm.
Makes sense, right? The clearer the robot's eyes.
The better it can pick out important details, features.
Which, in turn, speeds up its ability to make smart decisions. Smart inference, they call it.
So it's not just about seeing. It's about seeing well enough for the AI to, understand what it's looking at.
Precisely. And that's where deep learning comes into play.
Right, using trained AI models, neural networks, to analyze those images.
Yeah, to identify things like failed electrical components or maybe diseased trees in agriculture.
And the paper mentions using different visual systems, mono, stereo.
Yeah, single lens, two lenses for depth perception, stereo, even panoramic views, all feeding data into these trained artificial neural networks, ANNs.
Okay. And it also mentions pre-processing the images. Why is that needed?
Well, you need to make sure the images are consistent before feeding them to the AI.
Right.
Consistent size, quality, it helps the AI analyze them effectively, gives it a level playing field, you could say.
Got it. Okay, so besides cameras, the paper also talks about laser sensors. They provide a different kind of information.
They do. What's interesting is that lasers might not give you that rich, detailed picture like a camera.
Right, less detail.
But they are incredibly good at providing really accurate measurements of distance, depth, in real time.
So mapping the environment in 3D, but super precisely.
Exactly. Think of it like that.
And the paper mentions combining sensors, like a laser scanner with a regular camera.
Yes, sensor fusion. It says this combo, laser plus monovision, can actually be a faster way to get that sense of depth compared to using a more complex stereo vision setup with two cameras.
Interesting. And they use this in the grid repair drone.
They do. A really smart setup. They use vertical lasers to detect the vertical cables and then horizontal lasers to make sure the robot flies parallel to the power lines.
Using the best sensor for the specific job at hand. Clever.
Very. Then there's another crucial piece of tech. Thermal imaging.
Seeing heat, not light.
Exactly. It's not about visible light. Thermal cameras sense the infrared radiation that objects give off.
And the amount of radiation tells you the temperature?
Pretty much, yeah. The emitted power relates to temperature. The paper mentions different infrared spectrum ranges they can use.
And this is super useful for spotting problems in electrical stuff, right?
Oh, definitely. Because a failing component often gets hotter than it should. So it's like having a heat detector flying around.
A built-in fault finder.
You got it. Finally, just briefly, the paper touches on the basics of how these things actually fly. Rotor lifting thrust.
Yeah, the physics bit.
Just the basics. It explains the calculation involved, taking into account the robot's total weight, the number of rotors.
And adding a safety margin?
Yeah, usually around 20%, it says, just to make sure there's enough power to lift off reliably and handle, wind gusts or whatever.
Okay, so we have these incredible designs. They've got the sensors, the eyes, and ears to sense their environment.
Mm-hmm.
But how do they actually decide what to do?
Right, the decision-making part.
That's where the computer vision-based decision-making really comes in.
This is absolutely critical. The paper explains that for these robots, these embedded systems, to act intelligently, rationally, they need to interpret all that incoming sensor data.
And the algorithms, the computer programs they use for this are vital for speed and accuracy.
Both, yeah. You need decisions made quickly, but they also have to be the right decisions.
So the paper looks at kind of two approaches, traditional methods and then the more cutting-edge AI stuff.
That's right. Let's start with the traditional tools. What are we talking about there?
Oh, these are your more, let's say, established image processing techniques. Things like thresholding.
Okay, separating things based on brightness.
Yeah, or the Hu transform, which is good for detecting shapes like lines or circles.
Uh-huh.
And also Gabor filters combined with something called PCA, principal component analysis, for analyzing textures and patterns in space.
Right, the classical toolkit. And the paper points out these can sometimes be the fastest way to get a result, right?
They can be, so why not just stick with those? What's the downside?
Well, the main limitation is their adaptability, or lack thereof. They might work great in very specific controlled conditions.
And struggle with new images, or ones that are degraded.
Exactly. If the lighting changes or something looks a bit different, they can get thrown off. The paper gives an example, though, of successfully using the Hoff transform to spot those high-voltage power towers.
Okay, so it can work.
It can. And it also mentions using these classical tools for agriculture, assessing the green surface density in a field.
To figure out how much pesticide is needed.
Precisely. Figure 3 in the paper shows an example where they calculated the green density at nearly 50%.
Okay. But to get past those limitations, the field has increasingly turned towards, well, artificial neural networks. ANNs.
The famous neural nets. The paper says these are basically used to try and approximate how the human brain performs, how it learns.
Yeah, that's the analogy. In a very simplified way, of course. Sensor data goes in.
Through an input layer, processed through hidden layers.
And then you get an output, a decision or a classification. And the paper mentions the structure, input, hidden, output layers.
And the backpropagation algorithm, that's key for training these networks, isn't it? How they learn from mistakes.
Exactly. It adjusts the connections inside the network based on whether the output was right or wrong.
The paper also mentions the sigmoid function, often used for activation inside the network.
Yeah, especially for probabilistic stuff, like how confident is the robot in its decision? 0 to 1.
Right. But training these networks isn't always smooth sailing. The paper points out some potential challenges.
Like the vanishing gradient problem. That sounds dramatic.
It can be a real issue during training. Imagine the signals the network uses to learn, to adjust itself. They become incredibly tiny, almost zero.
So it just stops learning.
Effectively, yeah, it gets stuck. But the paper mentions a potential solution using a different activation function called ReLU, Rectified Linear Unit.
ReLU, how does that help?
Well, it's simpler. It outputs the input directly if it's positive and 0 if it's negative. This often helps speed up training and can avoid that vanishing gradient issue.
Okay, faster training sounds good. But ReLU isn't perfect either, is it? Something about dead neurons.
Correct. Because ReLU just outputs 0 for any negative input, sometimes a neuron can get stuck in a state where it only receives negative input.
So it never activates. It's effectively dead.
Exactly. It stops contributing. So the paper suggests a tweak. Leaky ReLU.
Leaky ReLU.
Yeah. Instead of outputting 0 for negative inputs, it outputs a very small, non-zero value, like a tiny slope.
Ah, so it allows a small gradient to flow back, even for negative inputs, potentially preventing the neuron from dying off completely.
That's the idea, keeping the learning process alive.
It's amazing how these sort of subtle mathematical tweaks can make such a big difference in AI performance.
It really is. And the paper gives a great concrete example using a convolutional neural network, a CNN.
Right, for identifying and classifying parts of those high voltage towers we talked about.
Yes, the CNN had 8 layers, and it achieved an average accuracy of around 89%.
Which sounds pretty good.
Especially considering they used a relatively small data set, only about 120 images for training, apparently. They used tenfold cross-validation to check it properly. Figure 5 actually shows some examples of what it detected.
Wow, 89% with just 120 images. That shows the power of these CNNs for image tasks.
Definitely. Even with limited examples, the AI learned to recognize these complex structures quite well.
Okay, one more really interesting application the paper explores. Detecting sidewalks. Specifically, sidewalks that might be partially erased or faded.
Ah, yeah, this was clever. They used a technique called wavelet transformation first, with a specific Mexican hat template to kind of highlight the potential sidewalk areas.
Mexican hat template, okay.
Then they converted segments of the detected sidewalk into simple codes, like vectors representing the pattern of, say, bright, dark, bright sections.
So turning the visual pattern into a numerical code.
Exactly, something like 1, NAC 1, 1. And these codes were then fed into a different type of neural network called a Hopfield network.
Hopfield network, what's special about that?
It's good at pattern recognition and completion. So they trained this network, which only needed 3 neurons in this case, to recognize the correct sidewalk patterns. Figures 7 and 8 illustrate this whole process.
And how well did that work?
Remarkably well. They achieved about 98% accuracy in classifying the sidewalk images into different categories: fully colored, partially erased, or fully erased.
98%, that's incredibly high.
It really is. It shows how you can tailor specific AI techniques like wavelets and Hopfield nets to solve very particular problems effectively.
It's just incredible seeing these, theoretical AI ideas being translated into such practical, sophisticated flying machines doing real-world jobs.
It truly is.
So let's try and bring this all together. After this deep dive into flying robots, what are the key things you think that we should really take away?
Well, firstly, I think it's crystal clear that flying robots aren't science fiction anymore. Not by a long shot. They're a rapidly evolving, very real technology.
Yeah.
And they have this vast potential to make our cities smarter. We saw examples from maintaining infrastructure, like power grids, to environmental care, like agriculture.
Absolutely. And this research really hammers home the vital role of AI, artificial intelligence, and especially computer vision.
Couldn't agree more. Those technologies are what enable these robots to actually do complex tasks independently. They need to see, understand their surroundings, and make decisions autonomously.
We also saw some genuinely innovative designs, didn't we? Like that grid repair bot working
Yeah.
midair or the liquid transporter, each one tailored for specific jobs.
Yeah, really specialized tools. And all of this is underpinned by, well, a really sophisticated mix of technologies. Advanced sensors,
Hmm.
actuators, the parts that let them move and interact.
And those cutting-edge AI algorithms making sense of it all.
Exactly.
It really makes you think, though, as these flying robots become more and more integrated into our cities, into our daily lives, what happens next?
Yeah.
What are the sort of unforeseen possibilities, maybe? And perhaps the challenges as well that might pop up in these increasingly automated urban environments?
That's a great question to leave things on. It's definitely something to ponder beyond just the impressive tech advancements themselves.
Yeah, the societal side.
Indeed.
Yeah.
How do we integrate this responsibly? What are the broader implications down the road? Lots to think about.
Dear viewer, your arrival here demonstrates your interest in our content. We invite you to subscribe to our channel. Thank you.